Okay, so today we're going to finish up the section we were on yesterday. We were on 13.1. And we talked yesterday about pressure, but never really defined pressure, so I'll start with that today. So one way to think of pressure is in an equation where it's force divided by the area. So for example, if you have a flat shoe, that's supposed to be a shoe, and you're pressing your body weight on the shoe surface, the area would be the sole of your foot. All of this would be the area. But if instead you are wearing a heel, now in this case, the area is a lot smaller. So there's a lot of pressure being put on the heel right here. And so that's why if you were to walk across a field with soft grass or a muddy area, the heel would sink into the ground pretty fast, because the amount of pressure you're exerting on the heel is a lot more than the pressure you would exert on a flat foot. In both cases, it's the same force, it's your weight. And so your weight doesn't change whether you're wearing this shoe or that shoe. So the force is equal to your weight, and that's constant. But what does change is the area. And if you decrease the area, like you do with wearing a heel, the pressure would increase. And with the pressure increasing, the heel sinks into the ground, while the sole that's flat doesn't. It's also why people wear snowshoes. Snowshoes are these huge, they kind of look like, what's the word you use? Tennis rackets. And they're designed to not sink into the snow. So if you increase the area of your foot, then the pressure will decrease. And by decreasing the pressure, you can stay top of the snow without sinking in. So that's what we think about force and area and pressure. Go ahead and clear this. I mentioned yesterday about this, that your tire is measured in PSI for pressure. So a normal tire, it's about 32 to 35 PSI. And I said yesterday that PSI stands for pounds per square inch. And the equation would look like this, where you'd have pounds divided by square inches. So pounds is force, square inches is the area. And so that's why PSI is a pressure unit, because it tells you the force in pounds over the area in square inches. So the tire pressure is due to the collisions of the air molecules inside the tire, and they're bouncing against the walls of the tire. So because these air molecules are in constant motion and they're hitting the walls of the container, in this case the tire stays inflated. So it's because the air molecules are moving around that they keep the tire the right size and the right pressure. If they were to stop moving, the tire would deflate. It's only because they're moving, exerting a force on the tire, that the tire stays in place. Air molecules go at about 1,000 miles per hour, and you have trillions of them hitting your face every second. And so these are going about 1,000 miles per hour, about trillions hitting a surface per second. That is what provides pressure in the air, in the atmosphere, and also in air-filled containers. In the atmosphere right now, it's about 14 PSI. And what that means is that per square inch of your body, which is not that big, if you were to do a square and each side was 1 inch, that would be a square inch. Per square inch of your body, you're holding 14 pounds of air of pressure. Now, you don't feel this because you're used to it, but you are carrying this pressure on your body. Every square inch of your body holds 14 pounds of air. So while PSI is used commonly in automobiles and things like that. Chemists don't usually use it. They use other units. So a common unit is a Pascal, named after Blaise Pascal. And a Pascal stands for a Newton divided by a square meter. So Newton is force. A Newton is equal to the weight of a medium-sized apple. And it's really just a coincidence that it's the weight of an apple. You know, Newton was watching an apple fall from the tree, and he asked himself, why does the apple fall down to the ground? And that question led him to the idea of gravity and the equation to determine the rate of the fall of the apple. But they named the Newton in honor of Isaac Newton after he had died. So this is just a coincidence that it is the weight of a medium-sized apple. So it's about 1/4 pound or so. So not a whole lot of force, not a lot of weight, but that's what a Newton equals. And as I said before, PSI is pounds per square inch. Not as commonly used in chemistry, but it is very commonly used in the United States especially. Do you have this down? Go and erase that. Okay. Now we can also have a kilopascal. Now, kilo means 1,000. So 1 kilopascal is equal to 1,000 pascals. A common pressure unit in chemistry is atmosphere as well. ATM is the abbreviation. 1 atmosphere is equal to normal atmospheric pressure. So it's the normal pressure that you feel just being in this atmosphere. And again, it's equal to about 14 pounds per square inch. Now there are a few conversions between atmosphere and other units. 1 atmosphere equals 101.3 kilopascals. Which is also equal to 101,300 pascals. So that's about equivalent to 22,000 pounds over a square meter. So think of a meter is about 3.3 feet. So think of a square 3 feet by 3 feet. There's about 22,000 pounds of air riding on that 3 by 3 square foot area. And that's the weight of a large semi-truck. Another conversion between atmosphere and another unit. This is millimeters mercury. So Hg is mercury symbol, millimeters. And this is because Torricelli, an Italian scientist, made the first barometer, and he measured air pressure using mercury. And it was 760 millimeters tall of mercury that he used to measure the air pressure. So that's where that comes from. We also call it 760 torr in honor of Torricelli. So a torr is the same unit as millimeters mercury. I mentioned before, 1 atmosphere is about 14.7 psi. So those are a few conversions that might come in handy in this chapter. We usually stick to a few units of pressure. You'll see for most of the examples, they're in kilopascals, but you might also see ones that are in torr or millimeters mercury. Let me go ahead and clear this. Okay, last thing to go through today is Gay-Lussac's law. We looked yesterday at Boyle's law and Charles's law. And there's a few more laws that we're going to use in this chapter that deal with gases. Let me go and just type this up faster. Gay-Lussac's law says that pressure varies inversely with temperature when volume remains constant. In equation form, it looks like this. P1 over T1 equals P2 over T2. So when volume is constant, P1 over T1 equals P2 over T2. So just the same as we saw yesterday with Boyle's law and Charles's law, you're going to be given variables. You'll be given 3 of the 4 variables. You'll have to solve for the unknown. Let's go through an example with this in your book. It's on page 448. It says that the pressure of an oxygen gas tank is 5 atmospheres at 25 degrees Celsius. The canister is located at Camp High on Mount Everest. If the temperature there falls to negative 10 degrees Celsius, what is the new pressure inside the canister? It's on page 448. So we are at the new conditions, the old conditions, and we solve for the unknown. So originally the pressure is 5 atmospheres, that's P1. T1, initial temperature, 25 degrees Celsius. And then the temperature falls to 10 degrees below 0 Celsius. So that's the new temperature, T2. And they're asking, what is the new pressure in the canister? So we want to find P2. Okay, so remember, it is very simple math. The only thing that could be tricky about this is remembering to convert to Kelvin. And that's really the only mistake you can make with these, is to forget to do that. So if ever you have Celsius, always add 273 to get Kelvin. So we get 298 Kelvin for T1. And we get 263 Kelvin for T2. And now at this point, we can solve the equation. So it's P1 over T1 equals P2 over T2. Okay, so P1 is 5 atmospheres. T1, 298 Kelvin. P2 is the unknown. T2, 263 Kelvin. At this point, we can cross multiply. So we do 5 atmospheres times 263. Then on the right-hand side, we get 298 Kelvin times P2. Divide both sides by 298. and solve for P2. So we can see with the units that Kelvin cancels out. We just have atmospheres left. So whatever pressure unit we had to begin with will end with the same pressure unit. So we don't need to convert between pressure units. We just need to keep it the same unit on both sides. So after we divide and multiply, we would get 4.41 atmospheres. Any questions about that? Okay. Now, let me look at your homework really fast for today. So I said 9 and 11. So let me go through one more thing, actually. I didn't realize I had one more section to do. It's very short. Let me clear this. So you need to do the combined gas law too before you leave today, which really is just adding up all the laws we learned in the last day. So it's a combination of Boyle's and Charles's law, as well as Gay-Lussac's law. So we take the three laws we've learned and combine them together into one equation. So it's P1 V1 divided by T1 equals P2 V2 over T2. And this combines Charles's, Boyle's, and Gay-Lussac's laws. Okay, for today, work on just two questions. On page 448, do number 9, and then go on to page 450 and do number 11. I'll write them on here too. That's question 9, page 448, and then 11, page 450. While you're doing that, I'm going to try to do the egg experiment again. It usually works on the first try. I don't know why today didn't do that, but hopefully it'll work this time. I'll let you know if it works. But you can work on the homework while I get that together. I want to show it to you tomorrow. I keep on trying it. I think I just wash out the bottle really well and let it dry out. So I'll have to do that today, and then tomorrow, hopefully it'll work. It usually works right away, but we'll have to wait until tomorrow. So today, just do your homework on 9 and 11. And then tomorrow, I'll go through a lab we're going to be doing on Friday with baking soda and vinegar. So if you have baking soda and vinegar at your home, you could bring it on Friday, and I can show you how to do the lab. It's really fun, and it's really simple. But if you don't have any, or if you don't want to do it, I can show you from my own what happens. But it would be fun if you had your own supplies too. We could do it as a class. So if you can, get baking soda and vinegar on Friday, but it's purely optional. You don't have to. Oh yeah, there's a question I'm seeing in chat right now, and the question is, can you have a note card with formulas on it for the final exam? And you definitely can. So I don't make you memorize any equations. So I think it's a really good idea to have a note card of all the equations that we're using in this chapter. Now, you can't label them though. So you can't say this is Charles's law and that's Boyle's law, but you can have the equations themselves. You can write down, today we talked about Gay-Lussac's law, and we had, what was that, pressure over temperature. So P1 over T1 equals P2 over T2. So you could write that equation down, but you couldn't write down Gay-Lussac's law next to it. And that's going to be, for all the equations in this chapter, just have them on a note card with you for the final exam, along with your periodic table, and you can have your polyatomic ions with you as well, sulfate, phosphate. Those can all be with you on the final exam. And also I have study guides for the final exam. Some of you already got them. If you haven't yet, you're going to get them pretty soon, either in the mail or delivered to your home. We'll be doing that next week. And some of you have Zoom meetings set up next week. Some of you had this week where you'll just have time to work on it and you can ask me questions. It'll be due for a grade before your final. But just like we did for the fall semester exam, you're going to have a final exam review packet, which about 45 questions or so for you to do to go over the chapters 6 through 13.